So now let's discuss different regularizers and the performance of align mirror descent. In align mirror descent for adversary bandit case, we restrict our set to a very simple simplex input domain. For instance, if we have 3 actions, we basically have simplex in 2D space. So this is P1, this is P2, and this triangle area is the simplex of 3 action case. Our remaining action 3, P3, is just simply 1 minus P1 minus P2. So this element can represent every possible probability vector on 3 different actions. So for this case, basically, when we think this space as Euclidean space, no matter our input is close to the boundary or not, we always think the distance between this and this is small, this and this is small, this and this also very small. But in a sense of Bregman divergence, what is Bregman divergence? Bregman divergence is this. And especially when x and y is very close to each other, then this Bregman divergence can be approximated by 1/2 Hessian of regularizer function pi x minus y transpose. Okay, so the distance between 2 points, or divergence between 2 points, is not just Euclidean distance, but that is scaled with Hessian at point y. For instance, in our example, beta parameterized regularizer function, what does Hessian? The Hessian of P is diagonal matrix, all 0 of diagonal element, and diagonal element having some P, K, beta minus 2 value. Beta times P, K, beta minus 2 is the diagonal element. So when P go to 0, as P goes close to 0, this value can have very huge value. Okay, so this element can be very huge as P go to 0, which means these operations can multiply the distance to very huge. So even if x minus y is very tiny in the sense of Euclidean distance, when it comes to Bregman divergence, the divergence between x and y can be very huge, especially when we close to this boundary. Okay, when we close to this boundary, then P3 close to 0, so the third element amplified a lot by this Hessian. When we close to this boundary, P1 value close to 0, so we have a very huge value multiplication on the first element and so on. Okay, so this Bregman divergence make a huge distance on the boundary, which can make your update very conservative way, especially for the boundary case. Okay, such regularizer make huge Bregman divergence near the boundary, and the regularizer so can make our algorithm more stable. Whenever our update go outside the constraint set, we have to learn some projection operation, and the projection operation is not stable element. Okay, let's look at this with another view. Let's think the step size eta is very close to 0. And so let's consider a very continuous model. Okay? Right. Then what is the, let's say, Bregman divergence? Okay, let's first discuss P dot T. So this is infinitesimal increment on the each element of P vector by the mirror descent rule when epsilon is close to 0. Okay, so from the mirror descent update rule, we know that P prime T plus 1 is equal to P T minus Hessian pi pt inverse eta x bar when eta close to 0. Why? From the update rule, we know that gradient of p prime t plus 1 is equal to gradient of pi function pt minus eta x bar. Here x bar is the update direction by the line mirror descent from the definition. So here, when eta is very tiny, naturally p prime t plus 1 and pt close to each other, right? So I think the Hessian at point p prime t plus 1 and Hessian of pt mostly the same, so we can approximate this area by some second order polynomial equation. So gradient of pi pt plus h is approximately gradient of pi pt plus Hessian of pi pt times h when h is very tiny. So from that, we can say that p prime t plus 1 is equal to pt minus eta times Hessian pi pt inverse x bar. Okay? So basically p dot t, the infinitesimal update on pt vector, is roughly, when we ignore this eta factor, minus Hessian pi pt inverse times x bar. Okay, so this is one interesting factor. Our updated rule is adjusted by inverse Hessian every time. Right. Then there are another very interesting factor. So how can we approximate the Bregman divergence between pt and p prime t plus 1? By the way, when eta is very tiny, eta goes to 0, p prime t plus 1 is almost the same with pt plus 1 because our update is too tiny. Our update cannot go outside of our constraint set, right? So p prime t plus 1 is almost pt plus 1. Okay. And this value from the definition pi pt minus pi p prime t plus 1 minus gradient of pi pt plus 1 p prime t plus 1 pt minus p prime t plus 1 in a product. Okay, so again, when eta is very tiny, so the difference between pt and pt p prime t plus 1 is very small. We can approximate the pi functions on that very tiny area using a second order polynomial using Hessian. Okay, and from that analysis, we can think so this is this is first order Taylor approximation on pi function at point p prime t plus 1. So we use p prime t plus 1 pi function value and the gradient of pi function at point p prime t plus 1, that is tangent line function at point p plus t plus 1. So the difference between this and this can be approximated using the Hessian. So that basically the Hessian of pi p prime t plus 1, and since we are using very tiny step size, this approximately same with Hessian of pt. Okay, so we are using very tiny step size to understand the Bregman divergence dynamic using mirror descent approach. So, and what is the difference? Difference is pt minus p prime t plus 1 here, and pt minus p prime t plus 1 transpose. Okay, so that is the lovely Bregman divergence between pt and p prime t plus 1. And from the previous page, we know that p dot t, the infinitesimal difference at time t when you use very, very tiny step size. We have this, right? So using this fact, this is approximately 1 over 2. So this is p bar. This is p dot t. This is again p dot t. We can use. Okay, this is minus p dot t, and minus can be cancelled out because we multiply minus and minus. This is essentially Hessian at time t inverse here, and x bar transpose. Okay, so in a sense of Bregman divergence, our updated length is proportional to inverse of Hessian matrix. Okay, previously p bar t, in the previous page, p dot t, the infinitesimal update of p vector, was controlled by Hessian of pi inverse, and accordingly the Bregman divergence of difference between pt and p prime t plus 1 also controlled by inverse of Hessian. Okay, so inverse of Hessian control our movement. So when we have a very tiny inverse of Hessian, our update becomes very restricted. And in this case, for the inverse of Hessian, when we use small beta, when we have beta equal to 0, in extreme case, the Hessian value will increase, right? Because p values less than 1, because we are using probability vector, and since this is negative, when this power term has a small value, as we have a smaller this power term, when we have less than 1 value here, our value becomes larger, and more importantly, as we use smaller this power term, we get more higher Hessian value. Inversely, when we have tiny beta very close to 0, the inverse of Hessian will decrease. Okay, so beta, smaller beta restrict our movement. Okay, so the update length becomes shortened. Okay, so when we have very high variance update, this inverse Hessian, this new Bregman divergence point of view help us to stabilize our update rule, especially for the boundary case. At the boundary, because of the pi additional regularization, our update rule follows some online mirror descent, and the online mapping control our update more conservative way, especially on the boundary when we have a smaller beta. But the problem is, this conservative way can make our convergence speed very slow. Okay. So the main goal of our update rule is we want to make PT go to P star if P star is the optimal point. Okay. So the distance between P star and PT from the definition, this is pi P star minus pi PT minus gradient of pi PT and P star minus PT inner product. Okay, so again, this is first order approximation of pi function at point PT, and this Bregman divergence at point 0 is initial distance to the optimal point. Okay, and since this is a first order approximation and this is the original function value, when Hessian of pi function is huge at time t and to the P star, if this Bregman, this Hessian value always high, then essentially the Bregman divergence to the solution is very huge. Okay, everything is proportional to Hessian of pi function. So in the previous case, our update changed the p-value location with probability with proportional to inverse of Hessian. So when inverse Hessian is huge, then our update has many jumps in the sense of Bregman divergence. But when we have very tiny inverse Hessian, our update length is very small, so we can get more stable update rule. But the Bregman divergence to the solution point is proportional to Hessian, not inverse of Hessian. So when inverse of Hessian is very tiny, which means our Hessian is very huge, which naturally implies the distance to the solution is high. Okay. Then what is the problem when we have a very high distance to the solution point? You know, the update length is proportional to inverse of Hessian, but we have very high distance because of high Hessian value. So naturally, intuitively, since the small, tiny inverse Hessian make a very tiny update, but the tiny inverse of Hessian make a very huge distance to the solution point, which means our update will take huge time to converge P star. It looks like we have to have very huge Hessian value, right? When we have huge, very tiny Hessian value. When we have very tiny Hessian value, we have very tiny distance to the solution point, and we have a huge update to the at every iteration. It looks like very desired property. But the problem is when we have very tiny distance to the solution and when we have a huge update at every iteration, which is just a random walk, we cannot convert to the optimal solution all the time, especially for the discrete time case. Every time we have a constant step size, we update PT using align mirror descent rule. Then such a huge update to make some oscillation, which cannot convert to the solution, but oscillate some very bad area. Right. And more interestingly, essentially, even for the continuous update case, so very tiny epsilon case, when we take this derivative, this is equal to x bar t p star minus pt, and which does not depend on the pi function. Okay, so which means every time our derivative on this Bregman divergence between true optimal solution and the current point does not depend on pi function, the regularization shape, which means our convergence speed only depends on the initial diameter. Okay, so that is also very interesting. But again, even if this does not depend on pi and the initial diameter just proportional to Hessian, so it looks like when we have small initial diameter can guarantee very faster convergence. No, this is not true. Since each update ranks depend on inverse of Hessian and update ranks is huge and high variance, we always suffer from some oscillation and some bad convergence behavior. So, high Hessian is required for stabilize our convergence behavior. On the other hand, low Hessian is required to make a low diameter at the beginning so that the convergence time from the beginning to the solution can be regularized. So that's why there is some trade-off between the diameter and the stability. When we took high Hessian regularizer function, then it is good to control our trajectory becomes more stable, but this is not good for initial diameter. On the other hand, if we use very small Hessian function as the regularizer, it is good to have a very tiny initial diameter, but in the sense of stability, we don't have nice property.